my great pleasure to introduce to you Danny Lange. I have known Danny Lange for almost 30 years. His travels from IBM lab in Japan to Microsoft in Redmond to Amazon, Uber.
Let's get going. Yeah, so I'm going to talk about simulation and its important role in AI. I've been working on various kind of agent technology for way too many years, and I spent the last 3.5 years at Unity, and having been at IBM and Microsoft and Amazon and Uber, which are all hardcore enterprises. I'm often being asked the question, what I'm doing at Unity, and the whole point here is actually that to really get to the next level of AI, we need to look at generating more data than the real world can actually give us. Yeah, so that's why Unity is interesting here. Very quick introduction of Unity. It's basically a real-time 3D platform. So it's a spatial thing used primarily for games, but also in a lot of other areas of AR and VR and film, etc. Yeah. So over half of the world's games are made with Unity. It actually runs on more than 4 billion devices, and we see 4 to 6 billion downloads every month, and we have over 2.3 billion monthly active players playing a game developed on Unity. Yeah, and we have about 3,500 people with headquarters in San Francisco. Yeah, so a very unique gaming platform. Yeah, so games have been used to drive AI research for a long time. Some of the earliest work is called Shannon in a computer chess playing program. He wrote an excellent article about it that he wrote back in 49, 50. Chinook is another one, is a checkers program. IBM Deep Blue, when I was at IBM, IBM Deep Blue defeated Garry Kasparov. Very interesting for Chinook and Deep Blue. The idea is to sort of have algorithms, have databases with openings and gameplays, and it's sort of all characterized by having some, really smart software engineering behind it, and some really nice designs, heuristics, brute force. When IBM Watson defeated the competitors in Jeopardy, it was really just a ginormous curated database of questions and answers. Yeah, so it was very fast to look up. Yeah, with DeepMind's AlphaGo, there's a kind of a change, because there we really saw reinforcement learning coming in, and we saw how AlphaGo and AlphaGo Zero, the later variations of AlphaGo, managed to basically beat the world champion, and later on managed to beat the system that beat the world champion through pure self-play. Yeah. So on the video game side, we have seen very important work on Atari games. We have seen Doom, Quake 3, Minecraft. Microsoft runs a lot of reinforcement learning challenges there. StarCraft with DeepMind and Blizzard collaboration, and very recently at Unity we released an obstacle tower challenge, which is basically a game designed to be played by computers. Yeah, but what is it with video games that's so interesting? Yeah, well, let's take a quick look at intelligence. It's something about acquiring and applying knowledge and skills. But the real intelligence we think about is the one that we find in biological systems. Yeah, so I'm gonna sort of take a pragmatic position there and say, hey, let's look around. Let's take a look at nature. It's things about eating and avoid getting eaten, and be careful to multiply, because an individual have a limited lifespan, so we need to carry on the species. We have to be aware of physics. So when we are out eating and we have to avoid getting eaten, we also have to be careful not to get injured. And finally, there's the ability to act upon the environment through agency. Yeah? So all of these traits are super beneficial if you want to survive in nature. And nature created this neurons, yeah, to equip animals, this infrastructure, yeah, through a number of chemical mechanisms, cellular structures, multicellular structures, movement, sensors. All these things evolved in nature to basically fulfill this need for intelligence to increase survival. Yeah. So if we think about it, when you have a real-time 3D engine, it's spatial, it has the 3 dimensions. It has a physics engine, so you're able to emulate gravity, inertia, collision. You actually also have a 4th dimension, which is time. So in a game engine, you actually have what I would call your AI biodome. Yeah. So what we did at Unity is that we made an open source framework for the Unity game engine, really addressing research in AI in primarily in reinforcement learning, but as I will show you also in a number of other areas as well. So what you do with ML agents is that you use the Unity game editor that all these game developers use out there. Just as a note here, we see about 500 to 600 games released every day on the Unity platform. Half of the App Store and half of the Android Play, Google Play. So you develop your ML agents equipped game or environment to test certain scenarios, certain learning things. We'll get back to that. You train, and in some cases, you actually may be able to deploy these models on devices. Yeah. It's open source. It's on GitHub. There's a bunch of environments that people can play with. Here's the link for GitHub. It has been out for almost 3 years. And here are a couple of papers that we wrote about ML agents and the obstacle tower challenge for reference. Yeah. So let's get into some learning scenarios. So I have these environments. Everything I'm going to show you today is based on standard reinforcement learning algorithms. PPO is one of them, for instance, and I'm gonna quickly sort of get into it here with the idea about reinforcement learning, which is to observe, take action, and reap the rewards. And then when you get the virtual cycle going here, you move from an exploration mode increasingly into an exploitation as you learn. Yeah. And I'm going to show a very little example here that I've done many times before. Basically have a system observe pixels frame by frame, give you 4 actions. The yellow chicken can move left to right, forward, backwards. There's a reward signal, negative for being hit by a car, and positive for picking up a package. Yeah. And otherwise it starts from tabula rasa. Yeah. So initially here you will see the chicken just randomly moving around more backwards than forwards, but in a moment it will actually pick up a gift package, which is a positive reward, and then instantly after picking up there, and then it got killed by a car. Yeah. So in a few seconds it already got 2 bits of information. Yeah. After half an hour of training, it gets pretty good at picking up packages and avoiding getting hit by cars. All the cars, all the packages are completely random generated every time. So it's not like learning, a certain sequence, and no, it has to actually generalize a bit and learn to wait and look for an opening. Look, after 6 hours of training, it becomes superhuman. It will pick up packages. It will never get hit by a car. No matter how random these cars show up, it will, as you saw there, it will wait for a moment until it clears up, then proceed. It'll become really, really good. Yeah. So this is the idea of everything I show you today. Yeah. So I'm going to show you some quick examples of what you can do with this. Like here you have a fairly complex situation of 8 joints in a quadruped, and basically by a simple rewards function here, which is make progress, move from left to right. Eventually, we'll learn to coordinate all all 8 joints in coordination. Yeah. Here's another example of a humanoid trying to learn to stand. There's a lot of variables here that needs to be figured out. It looks like a 12-month-old kid trying to learn to stand up. Yeah. Here's another example. The rewards function is basically move forward, and it turns out that to move forward, this somewhat looks like us running is pretty optimal for this particular geometry. Yeah. Taking this a bit further, here's the universal robot's arms learning to touch a cube, and the cube is just being moved around. Yeah. In all these examples here, it's essentially starting from tabula rasa, starting from scratch with a very simple rewards function, learn to accomplish some objective. Yeah. And it moves from exploration into exploitation as it gets better and better. Yeah. Let's take some more interesting examples. Curriculum learning is one of them. We found that to learn a difficult task, it's really a good idea not to use brute force, not to say I'm just going to throw more resources at it, but instead take a page out of Nature's playbook and basically say, hey, let's start easy. And as we graduate, as the agent graduates solving the task, the easy task, we basically incrementally make it harder. So in this case here, the agent needs to to climb a wall to get to the exit. Yeah, so the blue agent needs to get over the gray wall on the left here. And when the wall gets higher and higher at one point, it needs to actually use the orange cube, push it next to the wall and use it as a stepping stone. Otherwise, it can't get over. Yeah. So progress through this, basically, when you at any given stage, when you are good enough, you graduate to the next level. Yeah. What happens here with the learning rate? Brute force is the orange one. We just throw the agent into difficult task with a very tall wall, and it needs to figure out how to use the orange cube as a tool. Yeah. And it takes a while and doesn't really get good at it. The blue curve is where we actually use curriculum learning. Yeah. So we start out actually the wall is of 0 height, and the agent just learns to find the exit. And then we start raising the wall, and you can see at one point there's a drop, and that's when the wall gets so high that it needs to learn something new. It needs to learn to push the cube next to the wall and use it to jump the wall. Yeah. In practice, it looks like this. And I keep finding it interesting that these very primitive neural nets, they are able to learn things like using a tool like that from scratch. Yeah. We don't give it a hint. It just figures it all out. Yeah. When the wall is not that high, it will just jump the wall and not use the tool. Other examples where we take pages out of Nature's playbook, memory. In this case here, the agent comes into a room. There's a big cube. The blue cube is the agent. There's a big cube. If the cube is orange, it should take the orange exit, and if the cube is red, it should take the red exit. Yeah, and we just reward it with a positive or negative. Yeah. So what it actually learns is that it's the color that matters. It could have been the shape, the location, been many other things, but it actually learns that it's the color that matches. Yeah. Vanilla reinforcement learning wouldn't work here, because the moment that the agent passed the orange or the red cube, it would actually not see it any longer, and it would no longer remember its color. Yeah. So what we put in here is actually recursive net and INN, or an LSTM, that basically with some rate of memory loss recursively remembers the color of that cube it sees when it comes in. Yeah, so it's an example of memory. If we made this room long enough, it would eventually actually forget the color of that cube, and it wouldn't be able to solve this task. Few other things from nature, hierarchical learning. In this case, it's 2 machine learning models. One model is basically targeting the orange cube glowing over there. The second level of model is controlling the quadruped legs, as we saw previously. Yeah. So it's basically one model saying go left, right, straight, and the other one managing the motors of the legs. Yeah. Let's all these examples have been single agent examples. Let's take some multi-agent examples here. For instance, 2 agents playing some kind of tennis with each other. So basically, the rewards function here is to keep the ball going. Don't avoid having the ball hit the ground. Yeah. So it's a collaborative training here. Let's take another example that's adversarial. We got this idea to create a soccer example. So we have an offensive player. It's a striker, gets rewarded for scoring. We have a defensive player, gets punished if being scored upon. And then we put them together, and we have the offensive player not being very good at scoring, and we have the defensive player not being very good at defending initially. But as they play each other and play their roles, they get better and better, and they converge to some optimum. And then at that point, we actually just essentially copy the models and we clone them, and then we create 2 teams. And it looks like this. Yeah. So you have one team playing the other team. There's a striker and there's a defensive player. Yeah. Just quick note here: we never said that the defensive player should be a goalie, but clearly it's acting like a goalie. Yeah. And there are other interesting observations here, that the agents are running sideways because that gives them the best view of the field. Yeah, but the defensive players, they're just staring down the field. The little white thing is an eye that they use. Yeah. Other examples. Here we went a step further, and we did not give the players roles. We just basically said, you play together. You have a collaborative reward here because you have to play together and you have to win. And the interesting behavior you see here is that when one of the agents play offensive, the other one becomes defensive. But then when the other one gets the ball and moves upfield, it reverts, and the previously offensive player moves back into the defensive position. So they figured out a strategy of how to flip roles dynamically, which is really what we want. We don't want to instruct these how to solve that task. We want them to learn how to solve that task. So a peek into the future of multi-agent systems. Let me show another example here. This is 2-on-1. So the 2 blue guys are playing against the purple guy, which is supposed to be a goalie. And this is a typical training setup. What's interesting here is that the purple guy found out that the best defense is actually an offense. Yeah, is to basically try to keep the ball away from its goal. So it will not be in the goal and just waiting for things to happen. It will try to bring the ball away. So this is also people who play soccer, they actually know this. Yeah. Here I want to show you just a fun example where we have 2 humanoids that actually they're being trained from scratch again. Yeah. To run and kick the ball and try to get it away from each other. Just shows you that you can really train a lot of behavior totally from scratch. Yeah. Well, I'm talking a bit about traits because it's sort of it's a fun topic. A professor from the University of Washington once sent me this one here and said, well, I bet your deep neural network cannot do this. Yeah. And then he sent me this hamster here that was cheating on a maze. Yeah. But look at the wall example from before. Here's an old video I found where the agent basically just find out they just run around the wall. Yeah, so it cheats just like the hamster. Yeah, it's actually one of the biggest problems we have when we run these environments is that if there is just any way that there's a lower barrier to get to that reward, it will take it. Yeah, so it's an excellent way of trying to actually test systems. Yeah, so we got interested in traits. We are looking at extrinsic rewards, which are examples that you know from gaming. Yeah, capture, achieve, collect some points. You know, getting rich on something. Yeah, but nature also equipped us and animals with a lot of intrinsic rewards, like curiosity, the satisfaction from curiosity. Researchers know a lot about that. Yeah, patience, impatience, happiness, love, empathy. All these traits were evolved. You know, these intrinsic rewards are local. They're specific to the agent itself. Yeah. We compare that to like getting happy. Yeah. So nature gave us this desire for extrinsic rewards and intrinsic rewards because it's beneficial for survival. Yeah. So we played around with that a bit. We found some cases in standard reinforcement learning that are real troublesome, like sparse reward spaces. I call them Agatha Christie event chains. So it's basically ridiculously improbable scenarios. Yeah, we invented a scenario here that the agent needs to learn. It needs to enter a house with a bunch of rooms. In one of them rooms, a random button appears. It needs to figure out that it needs to push the button. A pyramid will appear in another room. It needs to knock down the pyramid to collect the gold bar on top of the pyramid. The gold bar is the extrinsic reward. Yeah. Random exploration will not work in this case. Yeah, it will not work. It will run 10, 15, 20 million episodes and it will not have learned anything. Yeah? So what we have to do is that we have to have some kind of agency here. Yeah, and the key level is actually intrinsic rewards. We try to say, what does curiosity mean? We think curiosity is something that you know, we see animals, they have it. They don't waste time. They search things out in a very strategic way. We do that too. Kids do that. Researchers do it. Yeah. And what we found is that we're able to express curiosity as the negative log of your reward in the context of a machine learning system. Normally what we want to do in machine learning is to minimize the error. Yeah, what we're looking at here is minus log. Yeah, what we're saying is I want to look around and the thing that I'm absolutely worst at predicting, I will pursue that. Yeah, so I will always pursue the thing I know the least about. That's curiosity, and that's what we express here. It's very easy to program this actually. So let's show a couple of videos. In this example, this is random exploration. Yeah, the agent is not very curious. It's just random Brownian movements. Yeah, and we're never really gonna get anywhere here. Yeah, so let's turn on curiosity, but without an extrinsic reward. So I'm not trying to get rich. I'm just trying to be curious here. Yeah, what happens? Well, it goes from room to room. It doesn't sort of get stuck in one room. It explores. It figures out that something happens when it hits the pyramid. So now I try to figure out, what if I hit it harder? Is something gonna happen? And I'm gonna get really hard here and see what I can do with this pyramid. Yeah, it's just curiosity. Now let's throw in the desire to collect gold bars on top, and the thing gets very determined, and something that it wouldn't have learned in 20 million, 30 million episodes, it can easily learn in maybe 10,000 attempts. It will basically learn this ridiculously improbable Agatha Christie event chain with curiosity in what in reinforcement learning would be considered very, very, very short time. Yeah, and he gets really good at it. Yeah. There's one caveat here, is that if you put a TV set in front of a curious agent, there's always something new to watch on that TV, and we call that the TV trap. And I'm not even kidding. The agent actually gets stuck there because the curiosity function really gets satisfied by just watching something new all the time. Yeah, because it never knows what's coming next. It's very interesting that you can play certain games, like the old Game Boy game like Breakout, where you shoot down bricks on top of your screen with a ball that you keep bouncing up, and you keep killing these bricks. And then you get to the next level, and then you keep doing that level after level. An agent with no extrinsic reward, so it's not getting rewarded for collecting points or winning games or anything. Pure curiosity, it will be perfect at playing this game, because it will have only one desire, and that is to get to the next level, because the next level is the most unknown. So it will play the game to get to that next unknown stage, and it will try to get to the next level, and so on. I want to show you quickly what you can actually have a character in a game trained this way. So this is basically a robot puppy I'm going to show you here that we trained using reinforcement learning. All the movements are learned from scratch, and there's only one rewards function here, and that is fetch the stick. Yeah, so it brings back the stick, and that's when it gets the reward. That's all it was ever trained on. I can grab the stick with the mouse and throw it, and then it will pick it up. Yeah. And nothing here is designed. It's not like an animation design that was in here or anything. So that's why the animation is not great, but this is actually basically created by training millions of episodes over and over, and the puppy gets really good at fetching the stick. I actually once did a demo where I tried to see if I could get the puppy to roll over by accident because of the physics. Yeah, so by moving the stick left and right, I was trying to see if I could get it to roll. And what happened instead was that it just grabbed the stick, turned around, and dropped it. Very, very similar to what I would experience a real dog to do. And it tells us something about how very primitive rewards functions derive behavior that we sometimes probably think there's way more behind that behavior than reality is. It's probably just a very brief set of loops in a set of neurons that basically just creates a very strong desire to grab that stick and return it to me, whether it's a mechanical puppy here in Unity or whether it's a real puppy. Want to change gears a bit here and talk about how this stuff here can be used in sort of some interesting areas, and especially with the pandemic right now. So we have seen simulation being used for decades. You know, people simulate the gameplay to figure out how to do things. Yeah, and what we can do in Unity, because it's a game engine, it's a real-time game engine, is that we can run these games which may no longer be games, but actually societal or industrial scenarios or research scenarios. Yeah, and what we did is that we got curious about this coronavirus, which everybody talks about all the time. So we started figuring out to design a made-up grocery store, and then start exploring whether different store policies have some reasonable impact on exposure rates. Yeah. So what we did was to design a store, a made-up store. In that store, there are shoppers. They're blue shoppers. They are healthy. There are red shoppers, they are infected, and then there are the blue shoppers, and those are the shoppers that accordingly to some model has been exposed to an infectious shopper. Yeah. So when we create a spatial simulation in Unity, first you create the environment as a 3D spatial representation of a defined space. You then add parameters in there, and those are the variables. In our case, say the number of shoppers, the number of registers, cash registers for checking out. The scenario is any given combination of these parameter settings that creates a scenario, and then there's an output. Yeah. So let's take a look at what it looks like in a particular example of this made-up grocery store. Yeah. This is the environment. So we basically model an environment. In Unity, you can actually import these environments from standard what's called design tools like Revit. So basically pull it directly into Unity. You get like a representation in Unity. That's the environment. We create some set of parameters, number of shoppers, registers, whether they're one-way aisles, and also we represent the model, the sprite model for the virus. We add some parameters for that. These are the scenarios, that's the values, and in this case there's sliders, so you can sort of play with it. And then at the very bottom you have the output, which basically says, you know, it's getting, you know, as you see in a moment, real-time updated over time. So let's take a look at that. Here we have a video. Shoppers are coming in. You look at the output measures, you know, you will see time going, and you will see shoppers leaving healthy and leaving exposed. Yeah. And now you can start changing the different settings. Yeah. And this is how we actually worked with the Institute for Disease Modeling in up here in Washington State on some of this, you know, had them do this, the sanity check for us. And what a lot of people, a lot of researchers are doing is that they will now sit and play with these variables and create different scenarios and look at them, and they will get some ideas. Yeah. But what's really interesting is that since this is really just running in a game engine that can run in the cloud, I can run, you know, I can run 4 simulations in parallel, and I can let systems like I just showed you in ML agents, I can let systems start exploring these parameters. Yeah. I can run 16, I can actually run tens of thousands of instances in parallel. And what I do is that I run all these different scenarios. I can do parameter optimization or hyperparameter optimization here. I can start figuring out patterns. And what happens is that I get a lot of data out that I can now do some analysis on. And in our case, we found that the number of infectious shoppers is one of the most important impacts on the exposure rate. Number of registers is important too. I was up in Whole Foods yesterday, and they had only like very few registers open, and the line to the register went through the shop, and I spent as long time standing waiting to check out as I spent shopping, which to me is like that last half an hour being in line. That's actually not, that's unnecessary. Yeah. And we see that numbers of registers actually matters. Yeah. We saw other things like how there's a relationship between exposure rates, number of shoppers and registers. And we actually found that we couldn't, in our demo project or conceptual project, we couldn't find any impact from one-way aisles. Yeah. Isolation, you can mathematically and statistically prove that one-way aisles are a really good idea. But in practice, the agents have to walk because they don't bring a nice shopping list that's ordered. So what they have to do is they have to walk more to get through the store and pick up the items when they're one-way aisles. It makes it basically just a longer process, and in that process you actually get as exposed as if you had two-way aisles, which I found interesting. But that was in our conceptual model or project here. You know, there may be other aspects that I'm not aware of. Yeah. what we did from an engineering perspective, I want to mention that, and that is basically some of the stuff my team is doing at Unity, is that we took a gaming engine that's designed to be on phones, consoles, PCs. We run on 32 platforms. So you write the game once, and it will run on iPhone, Android, Sony, PlayStation, Xbox, PC, Mac, you name it. Yeah, we took that and we put it in the cloud, where we can run thousands of these headless. We call it headless, and we run them not for humans to play the games, but basically for computers to play the games and for computers to capture the data. Yeah, and that now allows you to run all kinds of crazy scenarios of complex systems where it's either just not worth it, or maybe the system is so complex that you cannot model it mathematically. Yeah, so you basically run millions of scenarios to convince yourself that that your design or whatever is working. Yeah. Good. We have a bunch of we had a blog post on this. We have actually the simulator I showed you is in WebGL, so you can actually if you follow this link, you can actually play with it yourself. And we also made it all available open source, so the implementation is around. Yeah. Good. So some of the some of our biggest users of our technology is basically it's companies like DeepMind, Google's DeepMind in London. Very large amount of their work is happening on Unity. It's OpenAI, and the reason that these companies are using Unity is essentially that synthetic data is really king. In a game, you run at 30 frames per second. So in a standard implementation of Unity, that's 30 images per second. Yeah. If you ran on a single laptop and you generate 30 frames per second, you have ImageNet, which is 20 million photos hand labeled by people. You could generate that in 7 days synthetically. Yeah, just to give you an idea of scale here. As a frame of reference, 1 year of your life at 30 frames per second is a billion frames. When I was at Uber, we worked on self-driving cars. They operate typically at 10 hertz. Yeah, that's how they see the world. Yeah, and of course the physics guys out there, they know there's something called Planck time, which is sort of nature's frame rate, which is very small but discrete nonetheless, which is kind of interesting. Yeah. So what I'm trying to say here is that there's a lot of playing around with frame rates, and we get some freedoms when we move to synthetic data away from real world data. Yeah. Let me give an example here. This is an example of hand-eye coordination. You see the camera up to the right. This is work by OpenAI. And the camera sees the hand and the cube, and through reinforcement learning has learned to basically manipulate the cube. Yeah, so the camera sees, go through a neural network that controls the hand. Yeah, so you have a feedback loop. That was trained synthetically. Yeah, so it was not trained with a mechanical hand. It was trained using Unity. It took 300 billion frames to train this hand and get it to work afterwards in the real world. Yeah, 300 billion, that's 300 years. So actually you have like 300 years of experience done here, and they did it in about, I can't remember now whether it was 1 or 2 months on a bunch of servers. Yeah. Here's another example. This is a Rubik's Cube by OpenAI again. This one took 10 trillion frames. Yeah. So that's 10,000 years of nonstop video at 30 frames per second. Yeah. Shows the power of synthetic data. It shows you how we can beat nature in certain ways by scale and trickery. We can increase frame rates. We can run frame rates not at 30 frames per second because that's for humans only. But if it's a machine gathering data, there are all kinds of tricks I can do to scale up the frame rate to 3, 4, 5,000 frames per second. I can do massive parallelism, so I basically just run on thousands of instances rather than a single. And there's also some other trickery going on that when we train a machine learning model, that's a brain, yeah. We sort of blend the idea of species and individual. Yeah, we train a machine learning model on 10 trillion frames. That's 10,000 years of 30 frames per second, but the brain never dies. Yeah, it just keeps improving. Yeah, we can step back in time. This is actually something that's often being done, that you reinforcement learn something, and during your process, every hour you checkpoint. And sometimes the thing will, sometimes it will learn something undesirable or something happened, and you basically just step back in time and say, okay, let's redo it from here. Let's scale it. Let's move back, wind back evolution, and go and take a different path. Yeah, and then of course you can lower the frequency. You can drop the fill frames. Fill frames are the frames. It's an old Disney terminology that the key frames were drawn by the good cartoonists, and then the cheaper ones, they did all the fill frames in between. But we may not need all the fill frames. Yeah, we have the freedom of picking anything from Planck time to geological time when we generate frames. Yeah, so we can speed up the learning process a lot. Yeah. So that was a fast run through the idea of using simulation to advance AI. Some examples. Everything I showed you is open source and available. I think the important lesson learned, we're doing a lot of other things with synthetic data, but the key lesson learned is that real world data is a bit overrated. That synthetic data is actually really powerful to train computer vision systems for perception, to emulate physics and have robotic arms doing work, and to explore multi-agent systems where the agents are, assuming different roles, and you have some complex interplay. So that was what I had in store for you, and then I guess we are taking questions on chat or voice. Okay, I'm looking at the chat here.
I was muted. Yeah.
It says, can the links be shared? Yeah, I am happy to do that. Yes.
Plus, the whole video will be shared as soon as it's provided to us.
Okay.
You can move on, Danny. How do you ground the model so that the learning is meaningful?
Okay, let me. What did you ask?
Well, there's a question: how do you ground the model so that the learning is meaningful?
Yeah. It's that's actually a very good question. So first of all, I want to say that some of the key challenges we have found is that rewards functions, functional rewards functions, are very, very difficult to create. These agents will, at any given moment, as I demonstrated, cheat if they can. Yeah. So we have found over time that it takes a lot of non-typical, non-engineering skills to understand how to make sure that the learning you force upon the agent is actually achieving the desirable outcome. Yeah, we see a lot of emergent behavior. We had one example where agents are picking up some scarce resource, and it goes really well until the scarce resource is about to run out, and then the agents start going after each other instead, because that's how to prevent agents from taking resources away from you, where it suddenly become very aggressive behavior. There's another question actually around aggression, and we, yeah, where the two, where they in the soccer examples, there's also examples there of pushing and shoving, because there's a physics engine, yeah, and if you can push the other guy, that may be beneficial. So then when you have a rewards function, you may have agents that start going after the opponent rather than the ball, yeah, which is an undesirable, maybe probably an undesirable learning, yeah.
You want to read yourself, or do you want me to read you?
You pick. That's easy.
So from Barry Hoffman, the previous one was by Adam Drobot. The next one is taking the scenario with a dog. You mentioned basic behavior. Could you mix this up with a shop simulation and then addition to this and see, for instance, aggression in a stadium? So it's a follow-on to what you just explained.
Yes, totally. Yeah, that is actually so. So this is a very good question, because this is let me. I had it earlier today because we have a customer who's interested in modeling emergency evacuation or evacuation of a building, and you know there's fire, something happening, and people need to rush down the stairs, and what was brought up was that sometimes there's this behavior that someone is trying to get the opposite way. And what is the impact of that? What is the impact of someone taking the wrong exit? Do they pull a certain amount of people with them? Yeah. So that's where we are applying some of these mechanisms you have seen us to give agents in these simulations more diverse, unpredictable, and perhaps very human behavior. So the problem with these, say, evacuation schemes is essentially that that they are nicely thought out. And I'm an engineer, so sometimes I'm a little dismissive of engineers. They sort of think of the ideal situation, and every single person in that room are gonna do the right thing. Yeah? But no, they're not. Yeah? They are gonna have emergent behavior. They are gonna do the opposite of what they're supposed to do, and they may pull other people with them. So that's why it's so important to play very large amount of scenarios with a lot of varied behavior. Yeah, and then you realize that your solutions will never be 100%. It's just a matter of getting them to 80 or 90 or 95 or whatever, as good as you can, but you can never become 100.
Okay, the next question, Barry, we'll skip you. Have the third follow-on question, but we have to answer others. What information is related with curiosity, from Martinoni?
So what information? It's actually lack of information. Yeah. So basically what you do is, in the case of the agent in the room, is that we use observations, yeah? And there's a simple function from an observation. It's a policy, yeah? So it's an observation, and then I try to maximize my outcome by taking a next step, yeah? But what we're doing with curiosity is to actually flip it around and say the object I observe, the less I know about it, the greater is the uncertainty of it, and therefore I will move towards it. I will try to do something with that object, yeah, to actually build up more information about it, yeah. And when that is happening, there will actually now, it's like whack-a-mole, yeah, there will now be a new object around that I know less about than this object, and I will start pursuing that, yeah. And that's basically how information or knowledge is related to curiosity.
Okay, thank you. The next question from Nadeem Jamali. Is there something to model agents learning from each other, like people might?
Yeah. That's actually really fun. It's actually a pretty big deal. We got inspired by a very famous piece of biology or zoology research. It's like 3 years old or something like that. And the core here of it is imitation learning. Imitation learning plays an incredible role in nature. Yeah. And what these guys did, these researchers, they tried to train bees to pick food by pulling a string. They had to pull a string to get the nectar. Yeah. And they manually trained these bees. Yeah. And only one of them managed to learn it. It's very difficult, but they managed to train one bee to pull the string, get the nectar. Yeah. And what they did was that they put a jar of 100 bees next to it, watching how it would pull the string and get the nectar. And you can check out the paper. I can't remember, it was with 40 or 60% of the bees watching. They could now do it. They learned from one bee doing it. And even when that bee dies, the bee, the hive, the culture, it becomes a cultural phenomenon. The other bees will carry it on, and they will learn from each other. Yeah, we borrowed from that idea and added actually to the emulations framework the ability to have not only reinforcement learning but also imitation learning. So basically being able to learn from other agents' demonstrations or human demonstration. I did it for a small video game. 5 minutes of me playing the game made the agent as good as me.
Okay, you already answered the question, the first question of David Gonzalez, and that was your view of Hive type of learning with many units agents. But he's got a second one, and the impact that quantum computing will have in AI agents and development.
Yeah, so I have been, so I was actually on the advisory board for D-Wave for a while, and I have been very upbeat on quantum computing, especially because it's basically just using nature's algorithm to find optimal energy configurations. I think in reality, progress have been a little bit too slow for me, my patience. So long term, sure. Shorter term, it hasn't been easy, and we have not really seen much significant progress in that space. So for the moment, I'm a little pessimistic, but it doesn't mean that it cannot happen sometimes in the future, of course.
Okay, so the next question, how the checkpoints are chosen? Do you use successive features or other policy improvement approaches?
Yeah, just like nature, all of it. If you see these trees that in evolution, where you have things they just branch out, that's essentially what's going on here. It can be features. The agent change shape, but the agent change some capability. The agent learns, different policies. So in some cases, I have seen examples of something like 25,000 checkpoints. So they basically model it, visualize it as a big tree, and they basically go back and say, this branch here actually looked really good. Let's go in and explore this branch more. And you basically train agents in with different parallel policies. So you sort of branch out and really emulate evolution to a great extent with that approach. And it's very, very fascinating. And you can, as a human, go back and say, what if at that point in the evolution we change something, and then let's pursue that instead. Yeah, because we are like masters of the universe. Yeah, we control the paths. Yeah.
Okay, I think that that is all the questions that were there. I have one question for you. So you have been scaling quite a bit in the cloud, but there's also emergence of quite a bit of new accelerators, not just Google with TPU, but also Cerebras and many others, which are really breaking the grounds in terms of speed ups. Can you benefit even more so from them, or the traditional cloud suffices for you?
Yeah. So I belong to the school that thinks I basically think more is better. I don't think that there are of course certain things we can do where we can be smarter. We will always try to be smarter learning algorithms, optimize this and optimize that. But at the end of the day, what we have seen is a persistent pattern that more is better. That more data leads to more compute, leads to better models. We have actually researchers saying, you know, yeah, I train for 3 weeks, but I know if I train for another week, it gets even better. It's really, it's kind of addictive. It's very difficult to stop because it actually keeps improving. Not linearly, but still improves, yeah? So performance becomes the machinery behind all this, or machinery below all this becomes very, very important, yeah? Different kinds of optimizations, whether that's ASICs or other kind of accelerator architectures, become very, very crucial to sort of keep things up here. Right now, what we see is a massive scale out. Yeah, I think that I find it so interesting that OpenAI, you know, put a blog post out about how algorithms are getting more efficient. But at that same moment, Microsoft announced the 5th fastest supercomputer in the world dedicated to OpenAI. Yeah, and Unity is actually going to feed that computer with, you know, partly with image data and stuff like that, and behavioral data, as I have shown you today. Yeah, so there's definitely a need for increased, you know, offerings around accelerators of all kinds. Yeah.
I have a question, like quick question here. This is Lina Karam. So you mentioning like before, like the motivation behind the biology, and we're trying to model the neurons and the biological processes, but we know that humans and children, they learn from few examples. And AI hasn't been successful in doing this. We need a lot of data, a lot of compute, but the human body is low power. We learn from few examples. So what are your thoughts on this? We keep saying we're emulating the human, but not really.
Yeah, and that's I like you pointed that out, because if you look carefully at my presentation, I'm doing something really bad. I mix up sort of evolution and learning. Yeah, I sort of say, yeah, it's all the same. It's not quite, yeah. And the challenge we have in reinforcement learning is that by mixing this learning and evolution up, we always start from scratch. And that's why, say, OpenAI and Rubik's Cube, yeah, the hand. Well, that training of that hand starts from scratch, and you will train, you know, trillions of frames until that hand can now do Rubik's Cube single-handedly, yeah. And then you move on to the next project and you start all over, yeah. What nature is doing is that it creates some default infrastructure that and default wiring that we are born with, so we don't have to start all over. Yeah, so we are from through generations, yeah, millions of generations, yeah, we are primed for fine motorics in our hands, dexterity. We language are we good at, we object recognition are we good at. All of that stuff has been pre-wired. So what the baby has to learn, what the little child has to learn, is not starting from scratch, but starting with some pre-configuration. Yeah. So that's one observation. Yeah. So yes, our systems should get there too. And one of the points actually came up previously with a question around imitation learning. If agents can learn from each other, yes, that's what they should. So we should be able to. Imitation learning is super efficient because you're not learning from scratch. You're learning from an expert. Yeah, it goes very quick. Imitation learning is quick. Yeah. So you can do imitation learning, and then you can actually proceed with reinforcement learning from there. That's also way more efficient. Yeah. And in our obstacle tower challenge, the teams that performed the best. So there was an obstacle tower. You have to find your way through one level to get to the next level in the tower. There's 100 levels, and there's all kinds of challenges and you can fall in a pit and die, and you have to find keys to get to the next level, etc. It's just complex, yeah. The teams that succeeded the best were all not using brute force, but rather using clever combinations of techniques like imitation learning. They actually had humans show the agent how to do it, yeah, instead of just pure reinforcement learning. Then they use reinforcement learning to optimize it a bit and make it more efficient, yeah. They used actual perception or basic computer vision techniques, like instead of using pixel-based learning, they translated the pixels into an object abstraction so that the agent didn't just see pixels, but actually saw objects and planes in the building, yeah. So what they did was not cheating. What they did was building in knowledge into the system so that it becomes more efficient at learning, yeah. So I think that we're going to see a lot of work in that space, so that we don't have to, every agent doesn't have to learn from scratch every time.
Thank you. That makes sense. Yeah. Thank you.
Can you hear me now, Danny?
Yeah, I can.
Okay, I don't know what was earlier. I wasn't muted. So I always respected you not just for wisdom, but also for your taste for research. So you told us that quantum computing is probably not going as fast as you prefer. What are the areas that you advise to this community to go towards? What are the more promising areas?
Yeah, so I think that many, yeah. I think that multi-agent systems are incredible interesting, and I think we have not even scratched the surface. The behavior that I see in just 2-agent systems are mind-boggling. So that's something where I think that if you can really scale that out, I like to think about it this way, that that the human brain hasn't evolved for 70 to 100,000 years. Genetically, the brain is intact, kind of 100,000 years ago for Homo sapiens, yeah? So nothing, no Moore's law. There was no upgrades to the hardware. Yet we went from picking berries in the forest and hitting each other with, you know, clubs to put a person on the moon, yeah? So that's pretty impressive, yeah? So what happened? Well, multi-agent systems, yeah? We got better and better and better, yeah. And if you look at large corporations, you have large corporations that develop different ways of, you know, we have agile development methods. So the corporations that were all waterfall, they will sort of fall behind. So a lot of this organizational stuff is driving human progress. But what if I took that into multi-agent systems, and I'm not telling the agents what to tell each other. I'm not telling them how to cooperate. I just basically say to them, just like you learn to play soccer or learn these other things, can you learn to work together to solve tasks? That I think would is just extremely promising field, yeah, to mention one.
Okay, we do have one last question. Let's make it last. I'm not sure that I 100% understand it, but nevertheless, may I raise the question if there's time? Is there a difference between multi-agent and multitask learning when it comes to quantum computing? Examples, meta-reinforced learning, in terms of parallelization.
It's a good point, yeah, because what I don't know what the answer is, but when you have multi-agent, you could have agents that are given the rewards for accomplishing very specific tasks, yeah. So now you have like a multitask system, yeah, and these different agents need how to interact, yeah. But there's also another perspective where all these agents are very equal in their capabilities. Think about multiple robotic arms, yeah, where they may, in any given moment, one robotic arm may hold an object for another robotic arm to inspect it. Yeah? So they're all fully capable. They are literally multi-agents, yeah. So you see, so you can go multiple paths here when you look at it this way. I'm not sure how the quantum computing gets in there. That's
yeah. Okay, well, Danny, I highly appreciate all the time you invested. We're talking about a VP of AI of a corporation, and he found the time. So the IEEE really appreciates you spending this time.
I appreciate IEEE too. Been a member since, I'm not gonna say, 80s. It's terrible.